Hello, welcome to our next webinar. This is Daniele with me, an image engineer working at FilmLight, and I am Andy, a colorist. So I'm just doing the quick introduction today. The main part will be done by Daniele. And so he's going to talk about sRGB. And when we internally started with this topic, I came up with the analogy of religion. So we're dealing with a text that was written a long time ago, and there are different ways how to interpret it in today's world and life. And so there are different styles of how you can see it and how you can interpret it. And so I would say today, let's listen to evangelist Daniele Siragusano. And I will stay online and try to answer questions in the background and also collect the questions for the Q&A at the end of the presentation. So that's it from me. So I would say I hand it over to Daniele.
Thanks, Andy. This was kind of a good introduction. We haven't prepared this, so I'm quite surprised that it turned out this way, but good. I like surprises. Yeah, okay, so we're talking about sRGB. What is the issue, or what is the current state? The current state is that images that are graded in the grading room on a ITU RBT 1886 709 broadcast monitor or any other monitor or any other display standard does not really match when exported or rendered to sRGB, even with proper metadata tagging. And before we had proper metadata tagging, there were all sorts of issues with rendering for desktop publishing. I mean, we had this gamma shift because some interpreted a 2.4 power encoded image with a 1.95. There was this 709 1886 mismatch. But when we introduced the not long time ago a proper NCLC and NCLX metadata tagging, all of those big differences were solved, and then we were left with a few smaller ones, and we're going to tackle those. Why do we need to fix this? When I worked in post-production a few years ago, it was always the excuse for the client. So if you want to see the real colors of the image, you need to come to the grading suite, and this is where you can approve the colors and nowhere else. Well, in the current situation, and I believe also in the future, this excuse doesn't hold anymore because, yeah, we need to work collaboratively. We cannot freely move at the moment. So there is much more remote grading, remote approval, remote viewing done, and some of them are done on computer displays. So we need to get this right so that, yeah, the whole approval pipeline can work. And then, well, it's also a lot of content is consumed on actually computer displays with modern streaming platforms. It's not just the TV you're looking at, and TVs also are kind of computers nowadays. So so we cannot say there is the TV at home and the TV in the grading room, and the computers, they do not need to match. And also what we see is that there are more sRGB-like standards popping up very lately. The Apple Display P3, which is a slight variation of the sRGB standard in terms of the color gamut. So we really need to understand what's going on. And what are the issues? What are people complaining about, or why is it so hard to get an accurate color match on a client's laptop or a tablet? Well, there are two things. I think there's subtleties in the sRGB standard, if you really read through, and we will go through the important parts today. And there's also some ambiguity in current industry practice. That means when I say sRGB, what do I mean? What do others mean? And yeah, we also have a look at that. And then we see what the different strategies are for content publishing. Okay, let's jump into that. Let's have a look on the actual sRGB standard. It's always good to start from first principles. The sRGB standard is an international standard from the International Electrotechnical Commission, IEC. And the standard is 61966-2-1, the color management, the default standard color space, the standard RGB color space. And this was done in, I think, here it says 1999. So it's, I think, from 1997 to 1999. this standard was developed. So it's 20 years old. So just we need to remind this, because at that time we had different ways of working than we're having them today. Okay, so that's really important to get also the historical order right. Okay, so if we look into just already the table of content, and I just made a very just a grab of that little section. I hope I'm allowed to do that. Normally you cannot show standards or publish them, but it's just for educational purpose. Just the table of content, where we have on subsection 4, we have the reference condition, and in there we see, oh, reference image display system characteristics. Wow, they have defined a display. That's good. But then if you read further the table of content, encoding transformation. So we have in section 4 something that describes the theoretical display. And then in section 5, we have something that specifies the image encoding. And you could ask yourself, and you should ask yourself, why do I need to specify the image encoding when I already know the display characteristics? And a little spoiler, there is the pitfall. Okay, let's have a look on those subsections. In the sRGB subsection 4, it's the display is defined to have a pure 2.2 power law EOTF. So you have the encoded RGB values, and you raise them to the power of 2.2, and then you get basically the display light, right? So this is the EOTF function. There's no offset, there is nothing. It's a pure 2.2 power law. This is from the standard. So if a monitor can follow or cannot follow that in all of its details, because it's a little bit more complex if you look on how LCDs are working, and I'm not the right person to talk about the inner mechanics of folding S-curves of LCD drivers and all of that. So others should do that. But in this standard, we have a pure 2.2 power law defined with no offset. Okay, if we look on the section 5, so if we go through this French and English text there, we come with the encoding function. And the encoding function is a little bit more complex because it defines a linear part in the shadows below a certain point. So the point is 0.04045. And below that, we have a straight line. So it's basically just a straight line. And above that, we have another power function, an exponential function, but it's offsetted and scaled so that these two functions will meet at that cusp point here. And this function is also used in Baselight when you select at any point in the color space journey sRGB tilde 2.2 gamma rec 709. And a little spoiler, there is this little attention thing, which you will not have in 5.2, but in 5.3. So another spoiler here. And this little tilde symbol here just symbolizes that it's not a pure 2.2 power function, but it's something that approximates a 2.2 power function. But the devil is in the details. So I like to think about those functions always graphically. So let's do that quickly. So if we zoom into the shadows here, so we have nominal display linear light here and the encoding function here. And yeah, we see that straight line here. This is the lower part of the function. And then we have an offsetted 2.4 power law function there. And here in that point, we basically have the same slope in both functions, so we can transition nicely from one to another. And this is what sometimes it's called the compound function, because it's spliced together, or piecewise defined function. And it has a linear part in the shadows, and then it follows a power function. And the net result of that, if we zoom out, and now we're looking from the 0 to 1 range, here, and the normal encoding. So the green one is the sRGB compound function, and just as a reference, a pure 2.2 power law function is the red one. And we can see, sometimes the red one is above, sometimes it's below, but well, it's approximately a 2.2 power law. But again, let's have a look in the shadows. So if we zoom in again on the shadows, we can see that actually down there, and now I don't need to zoom in that much actually. So that would be, if you multiply this by 100, this is 2 nits. I guess. Yeah. And so we have already the discrepancy, which is quite high between a full true 2.2 power law and the sRGB encoding function. Other way to look at it is if the display has a pure 2.2 power law and the image is encoded with something slightly different, how does the mismatch of both look like? This is something we could look at. And this is what I'm trying to do here. So this is now nominal display light versus nominal display light. And if we would have no mismatch, then it would come out as a straight line where 0.4 is mapped onto 0.4, or 4 nits is mapped onto 4 nits, and 10 nits is mapped onto 10 nits, because we have a distribution pipeline or an image pipeline, which is absolute, basically. So now if we look at the encoding decoding mismatch, we can see that from zoomed out, it looks quite good. It's almost a straight line. You would not even notice that it's not a straight line if you would not have that blue line below it. But again, if we look a little bit into the shadows here, and now I don't need to zoom out. Now I'm at 10 nits here, and I'm seeing that, well, it's a little bit darker. So the encoding decoding mismatch makes the image darker in the shadows. And we all know that linear light is perceptually not really relevant. So what if we scale both axes with a little bit more of a perceptual function? So I'm using basically a power function here to scale the coordinate system. So it's an exponential coordinate system. After this crisis, everyone knows what exponential growth is. And exponential, we all learned how to read exponential graphs. So that is, you could say that this is a little bit more perceptually meaningful. And what we can see is that the higher we go, the less that mismatch really counts. But in the shadow, actually, there is a big difference. So you could ask yourself, well, why the hell are we having this kind of mismatch? And isn't the sRGB standard aware of that mismatch? And in fact, you only just need to, in the introduction of the encoding function, it's already discussed that there is a mismatch, and it's on purpose. I'm just reading that small paragraph. One impact of this encoding specification is the creation of a mismatch. Well, yeah, that's true. Between theoretical reference display tree stimulus values and those generated from the encoding implementation. The advantages of optimizing encoding outweighs the disadvantages of this mismatch. A linear portion of the transfer function of the dark end is integrated into the encoding specification to optimize encoding implementations. At that time, 8-bit processing was basically the norm, and that linear part really stretches out a little bit the code value space, because a pure power law has an infinite slope and when it goes to 0. And in this context, it makes a lot of sense. It's actually, the piecewise function is a good function. So we can say, and also it did, I'll say this later. So sRGB carries an implicit flare compensation in the inner of its standard by defining two functions, one for image encoding and one for image display. And if you think back at the time with the ITU RBT 709 specification, where you had a camera which encoded something very different to what the display characteristic was, at that time, this was kind of a modern approach to color management, which is implicit color management, because you don't need to, not many people need to know about this, and you can put all of the complex stuff into the camera. So you have only one expensive kit, and the displays can be rather stupid. So not much electronics in the displays at that time. This was the case. So the system gamma, the video system gamma was, it's kind of a similar approach where you do some implicit stuff to achieve some of your goals. Okay. So you can say that sRGB has a flare model, and in fact, if we compare the mismatch of like that flare compensation with the flare model in TCAM. TCAM is FilmLight's display rendering transform, and I just stripped everything out and just had a look at the flare model and plotted it in the same graph. And you can see that if you render an image from scene referred to display referred with TCAM, you get actually something very similar as if you would have that mismatch in the encoding and decoding. But again, in the year 2020, flare compensation is part of the display rendering transforms. All the DRTs have some sort of flare compensation built in, and it should not live in the distribution pipeline of a single distribution channel, because we are in a multi-distribution, multi-channel environment at the moment. Okay, so so if there is a mismatch and this flare compensation going on all of the time, so how is it lived in the industry at the moment? So we made a little survey. I think there were like 24 participants. We had camera manufacturer, display manufacturer, software developers, application developers, distributors, color consultancy, engineers, calibrators, colorists, and we asked a few questions. And let's have a look on the questions and the answers. And this should give us a little bit of a feel on how the current state in the industry is. It's not a really big survey, but it should just give us an idea. At least for us, it was helpful. And I want to share this. And I want to also thank everyone who actually participated in that survey. So we ask, when a third-party monitor claims to be an sRGB, which physical EOTF do you assume it follows? That means, the question means, if you cannot control the monitor, so it's a third-party monitor, so you don't know what it is and you couldn't measure it, and it's labeled as sRGB, what do you expect? What physical EOTF does it follow? And 50% said like a plain gamma of 2.2. 31% said the compound function, so the encoding function. And then we had got some others, any of those, let the user assign a color space. I assume it's implemented differently by different manufacturers. I would not assume if possible. Okay, so most of them are aware that so these are aware that there are differences, but I would say the majority, you can say, is expecting a third-party black box monitor to follow a 2.2 power law. Okay, for display manufacturers, what is the physical factory calibration EOTF of your monitors in sRGB mode? For calibrators, which physical EOTF do you calibrate the monitors for the sRGB mode? That means, so now if you can control the monitor because you either build it or you calibrate it, what are you doing? 30% say a plain 2.2 power law, 21% says a compound function. But then we got basically some of those slices go to the plain pure 2.2 power law, mostly plain 2.2 power law. On the Visual Effects Studio, we move to 2.2. We do not include that wording. We get sRGB in our monitors was one where it's either 2.2 or something else. So we would say that the majority of display manufacturers and calibrators are tending to calibrate towards a 2.2 pure power law. So we can say that on the display side of things, it seems that the majority is living the standard as it was designed over 20 years ago. Now let's look on the encoding side of things. For software developers, when you encode and render an image to a file in sRGB color space, what do you really do? And for the users of software, what do you think your software does when you export images in sRGB color space? Well, 20% said, I expect my software to use a plain 2.2 power law, and the rest said, I expect, or actually I'm programming my software to use the compound function. And yeah, there was one saying that it uses a 2.4 gamma function. Okay. For software developers, when you decode an image, so the first question was more like on the creation of files, like when you encode something, and now the decode side, because there you need to do an assumption. If you get an sRGB tag in a file, what do you do? When you decode an image from a file which is tagged as sRGB color space, what do you really do? For software users, what do you think your software does? And here it's also 30% said my software decodes the image with a plain 2.2 gamma. My software decodes it with a compound function. Then we also get like, and this is the majority. It's not far ahead, but it's always those 50-ish, a little bit more percent where you could say that already gives a majority. Yeah, my software decodes with a 2.4 gamma function, both encoding and decoding. I'd expect software to use the sRGB compound function. So this slice goes over here. So we get like the majority again. On the decoding and encoding side, use the compound function. Okay. This is an interesting question for content creators. What do you do when you create content for internet consumption? Because this is also a trending topic. What should I do if I upload something to YouTube and Vimeo and other platforms and for review and approval? 50% just said, I just reuse the content mastered with a 2.4 power law in my dim surround. I just take that file and send it over there. And we will have a look at this. That's certainly a valid thing. I create a separate master in sRGB color space. So I assume it's encoding with the encoding function. I work in post-production and we never render to sRGB. Clients are unaware of these differences, reusing the 2.4 gamma, video content 2.4 gamma. So we got even more slices on the 50% side. So the majority, we can say, are just reusing the video master for internet or for desktop consumption. So to summarize this, most users calibrate the monitors to a pure 2.2 power law. Most users encode, decode their images with the compound function. Most users reuse their ITU BT186709 masters for sRGB deliveries. And also what we can say is sRGB is an ambiguous term because it defines two things, the display and the encoding. And many users, especially in production, complain that images are too dark in the shadows when exporting to sRGB. Before we move on to actually some practical examples, just a word about BT709 and sRGB, because sRGB was designed, and this I think is important to understand, that whole thing was designed with the compatibility to ITUR BT709 in mind. But BT709 is the Rec 709 camera, right? It's not a display standard. In fact, sRGB was the first official standard which standardized actually a display that goes along with the BT709 camera. So it was the first display standard. But then later, I think 10 years later, roughly, or a little bit more, the ITUR BT1886 recommendation came along and defined flat panel EOTFs that should be used for evaluating HD content. And it defined a 2.4 power law. There is an offset in there, but on the encoding and decoding side, we could keep the offset always to 0.0. So at least for me, BT1886 is the same as, say, a pure 2.4 power law. Okay, many see the mismatch of a 2.4 power law grade, like an image I've mastered in a dim surround on a monitor, and then I just take that image and stream it on a 2.2 power law sRGB display, and there's a mismatch. This 1.1 gamma mismatch is what I'm going to use for the surround compensation, because we expect that sRGB is a little bit brighter than what the grading bay, and that mismatch actually is the surround compensation. And it seems to work because a lot of people are reusing their video masters for for sRGB or for bright surround. So there's no need to render it, it might be. So sRGB is optimized for 8-bit processing. sRGB has a mismatch. This is a small in the middle summary. And the mismatch tries to compensate for flare and is optimized for a camera. So you take a 709 camera material and then it kind of work. But the sRGB encoding decoding mismatch is not really desired if the image is graded and approved via modern scene referred multi-delivery workflow. So fast forward to today, where we have DRTs and other color management frameworks in place, we don't want any implicity in our pipeline at all, because nowadays implicity just makes things obscure, and if things are obscure, they are confusing, and it will not get right. It will not be right. So I'm a big firm believer of transparency in complex systems. You show the complexity, but at least it's transparent, and you give the users a chance to actually understand what's going on. Okay, so you can use the BT186709 as a sRGB delivery. That's fine. Wait, you need to. There are some subtleties again. If you use the 709 master for your sRGB delivery, you need to be aware that you're getting three things. You're getting a reasonable compensation for the different surround, bright surround and dim surround. Fair, yes. But also you get a slight desaturation and hue skew in your colors because you're doing a 1.1 power law operation directly on RGB values. So you're changing the RGB ratios, and that is causing a slight minimal. I'm honest, it's not very big, but we have a look at it, how big it is. But you need to be aware of that. And also, you haven't solved really for the other evolving standards like Apple Display P3 if you just rely on implicit color matching. The desaturation and hue skew effect is small, and the viewer will adapt to it, I believe, because we still have this thing of adaptation going on. But still, for critical image analysis, if you have a remote grading, remote viewing session approval or with JPEGs, you send them over, where you actually want to talk about the fine nuances of colors, this might be not ideal. Okay. Okay, let's have a look. So we look at one image in the different surrounds, and I first explain the setups, and then I try to beam you in those setups with a little bit of some surrounding tricks in order to make this work. I encourage you, if you have the chances, if you're either in a late time zone or if you can close the curtains, I would encourage you to close the curtains and close all the lights, because I need you in a really dark environment. And if you cannot do this now, we are posting this later on the website, and then you can rewatch that thing. And I will do the same. So I will turn off all my lights. So in Germany, it's still a little bit bright outside, but I think it's okay. And I really encourage you to do the same. And it's also, it's not the full real story I can show you, because the field of view via a go-to webinar platform is not the same as in the real world, but it's good to have a look. Okay, so first we have a look at the reference, and the reference is an image which is scene referred image, and we using a display rendering transform. I'm using TCAM in this scenario. With a dim surround transform compensation, I encoded with a BT186709 into that color space, and then I'm displaying it also on a color space on a display which is exactly a match to the encoding here. And then I put you into this dim surround, and then I need to do some little hacks so that in the that it goes over the webinar as well. But trust me, what you are seeing is if you would look on a 2.4 pure power law monitor in a dim surround. Then we have the case one, which is probably some of our customers and you maybe have also went into this with unsatisfactory results, and I hope now we can understand why they are like they are. So we take the scene referred image. The goal is to be in a bright surround on an sRGB display, and we assume now that the sRGB display is a pure 2.2 power law. So what we do is we take the scene referred image, case one, we use the dim surround DRT because we might not have a DRT that has a compensation alternative. Like there are DRTs that don't have an explicit bright surround compensation version in their DRT family. And then we are also encoding it with the compound function. And then we are with the piecewise defined function. And then we are displaying it on a pure 2.2 power law display. So we got the wrong DRT because it doesn't compensate for the surround. And then we're also getting on top of that the additional crushing in the blacks because of the mismatch of the encoding and decoding of the image. So this will be case one. Case two is we are using a DRT which has the bright surround, so we're doing the right thing on the production side of things, but then we are encoding it into still the compound function. So we see if the DRT tries to compensate for that, but then the mismatch of the encoding and decoding kicks in, see how this works. Then case 3 might be also something, if I don't have a dim surround a bright surround compensation DRT, then at least I could encode the image in with a pure 2.2 power law. So this is case 3. So DRT, dim surround, there's no compensation for the bright surround. And then we are encoded with a pure 2.2 power law encoded image and then displayed on a pure 2.2 power law monitor. Because we have a match here and we use the same DRT, this is actually exactly the same as if you would take your video monitor and if you would bring it into a bright surround, because the light energy that comes from the display is exactly the same as in your original on your original grade. That would be, that case 3 is actually absolute luminance preserving. What was 5 nits on your grading monitor is 5 nits on the viewing. And we know because there is no surround compensation, that might not work as good. Case 4 is what a lot of people use for their final deliveries when they do reuse the video master for internet consumption. So you take the scene referred image, you use the DRT, which has not a surround compensation for bright surround because it's still the same you used for grading. And then you encode the image to BT186709 with a pure 2.4 power law, but then you just declare this as my master. So you're actually not changing the code values in the file, but you just say, look, just stream this on the monitor, on the 2.2 power law monitor. And then you get a mismatch between the encoding and the decoding because they're two pure power laws. The mismatch is 1.1. And this you will use as your implicit surround compensation. And then case 5, the last one, if we take a DRT with the proper surround compensation in production, we encode the image into a pure 2.2 power law encoded image. We tag it as sRGB, ready for internet consumption. We have no tweaking in the display distribution pipeline. And then we view this in a bright surround. Okay, let's get into this. So this is our reference. I just showed a few seconds. So of course, I've chosen an image with a lot of skin tones and also dark details, because these are the two things we want to have a look at. If you have been in this problem space, you might have noticed that for normal exposed or lighter exposed images with not much of dark content, that actually is not a problem at all. It only shoots you in the foot if you come into those few scenes which are really dark graded but look great on a rich high contrast OLED display, and then suddenly you see the lag. Okay, so I hope you are in a dark environment and I give you a little bit of dim surround feeling by putting that frame into a 5 nit surround. And now let's have a look on case 1, where we use the DRT with no compensation. We encode it to sRGB, but the encoding function, and then view it on a pure 2.2 power law monitor. Okay, this is how it looks. Yeah, and this is, I think some of you will see this in a very familiar way, because there are a few also larger workflows out there, color management workflows, which have this in, and you can see all of the details in the shadows are gone or compressed. And if we go back here into Baselight, if we have a look on the Luma waveform, between 1 and 2, we can see that because of that flare compensation, you see that the shadows actually are getting not clipped, but they are compressed a lot. Okay. Let's go to case 2. Case 2 is when we use, let's say, TCAM with a bright surround. This is already an improvement, so because it tries to make that surround compensation, but it really cannot fight against against the flare, the additional flare compensation, which should not be in the pipeline. So if you go again, reference 1 and case 2. So this would be the case for in 5.2, and I think that is the current state, unfortunately, is that if you render to sRGB to the encoded function with the correct DRT, which does the compensation, but then the implicit flare compensation is working against you. So this is basically also current state. Not ideal, especially for dark images. And we see also the perceived saturation is getting increased because of that RGB nonlinear transformation, again changing the ratios in the blacks. Okay, so case number 3. Let's have a look on the Luma waveform here. So the Luma waveform does not represent the encoding in the image, but the light energy that you would measure from that display. So, and you can see that case 3, where you encode with a 2.2 power law function, and you just make a colorimetric transformation to 2.2 power law. Actually, this is absolute luminance preserving. The only thing that changes is the surround from 5 nits to something like 30 nits here in this scenario. Okay, and if you look at this, the image stays exactly the same, but because of the bright surround, I hope you see that the perception of the blacks is getting different. So you see the blacks are, it's not that you see not as much of details, but the image looks overall more contrasty. And if you would do this in a even brighter surround and with a larger field of view that covers your surround, that would be actually even more. Now let's have a look on case number 4. Case number 4 is you take the 2.4 graded master and you just say to the display, this is already ready to be streamed. So you have a mismatch between a pure 2.4 power law and a 2.2 power law. And we can see the image gets brighter. So if I flip again, reference. And this making the image brighter, this brightening, this gamma mismatch is actually helping to keep the perceived contrast the same. It's to some extent you could explain this with the Bartlett-Brennemann equation, with some color appearance phenomena, and so on. But what we also can see is that we are, if I flip here between A and B, what you can see is that, so this is the reference. This is the image resulting and due to the mismatch. And you see that it's getting desaturated and also a slight U shift. And that U shift, every colorist knows that if I'm touching the gamma in video land, then I'm getting this intermix between my colors and my brightness, because I'm just modifying RGB values with an exponential function, and that changes the saturation and also the perceived hue. So what we see here, that, and maybe I can zoom in a little bit more. So this is 1, so this is the reference, and this is the 2.4 reusing the video master. It's not much. I would say this is a little bit more red. This already goes into orangey colors. I think for final consumption, yeah, you will adapt if you don't know, if you don't have this reference here. And this is a very artificial setup here. And I would even say that if you have one monitor in one room in a dim surround and the other one in a bright surround, and you need to go over a hallway to the other, then you would need to know the content very well to actually spot a difference, I believe. Okay, so now let's say the last one, case 5. So between case 4 and case 5, we can see here. So this is basically using the surround compensation in the display rendering transforms in a hue preserving manner. So it pins basically the colors and just makes a compensation for the surround. So this is now the reference, and this is now with the bright surround. And also, as we can see here, if I flip between the two, the actual hues and the saturation stay the same. They are only nudged a little bit brighter to compensate for the surround. So this would be scenario 5. So the summaries. Oh, now let's get to what should I do from now on. So just a summary, some objective observations. sRGB standard needs some updating for scene referred workflows. It was designed in a time where there was no scene referred, or its scene referred workflow was only used in the film lab, or indirect scene referred grading on emulsion based workflows. sRGB encoding function, like the piecewise one, should be avoided, I believe. It's not yeah, the time has changed. We don't need implicit building blocks. I should turn on my lights again. What we don't want is our implicit color management building blocks in certain distribution pipelines. It just causes hassle. Yeah, and then we should all agree on a new term, which is sRGB display. Just saying like it's the sRGB standard, but the display section of it, if we are talking about a pure 2.2 power law. So if we just be a little bit more precise about our wording, then I think we can, yeah, this is enough updating for the standard to survive a little bit longer. So we propose the term sRGB display should be used when referring to the pure 2.2 power law EOTF to avoid ambiguity. So distribution strategies, you can reuse the video master for sRGB if you accept a small saturation and hue change. I encourage you to do the experiment yourself, have a look at it and see if you can live with it. Yeah, but the video masters needed to be treated already as encoded for sRGB display. So you should not take the video master and then transcode it, because that would be then case 3 or case 2, and that would not result into the right color. So no further conversion, please. And for color critical applications, like you might see in near future in your color grading system, and if you have someone connected to that system and has an sRGB display, and you can have a different streaming, a different stream to that than what you are viewing on your monitor, which might be possible as well, you should use the sRGB display viewing color space for that stream. And yeah, so for remote grading, or if you render approvals for still frames, you can, if you use a DRT which has a bright surround compensation like TCAM, you can use the sRGB display for viewing color space. So what does this mean in Baselight? In Baselight, this means the compound function with it indicated with this little tilde symbol becomes obsolete and lives, is it her or his or it's pure life together with the Rec 709 display referred camera color space in the orange corner of your color space list, and you shouldn't use it for viewing or rendering. It stays in there for compatibility, because if someone gives you an image and says, well, I have encoded it with a compound function like a title or something, then you might use this color space still for input on the input side when you tag material. That's why we kept it in the color space menu. But you should avoid it for viewing or rendering if you're following a modern scene referred workflow. We will have a new color space called sRGB display, then 2.2 gamma Rec 709. No tilde means it's a pure 2.2 power law. And also it will set and trigger the correct sRGB metadata for NCLC and NCLX and all of the other metadata systems. So the next one in the chain will believe it's an sRGB image, and hopefully and most certainly it will just stream it to the sRGB monitor. The new sRGB display 2.2 color space should be used for remote viewing, yeah, if you're connected to a sRGB display, or for rendering for sRGB deliveries. And this the same applies for the Apple and the Adobe color spaces we are already shipping, the Apple Display P3 and the Adobe. I mean, Adobe already was very close to 2.2 gamma, but now both are plain 2.2 power law. Yeah, so these were changed as well. So my last comments until we get to the question. Yeah, I tried as hard as possible to avoid the term gamma because it's not really describing anything in a mathematical correct way. And even in the sRGB standard, there was a mentioning that gamma is confusing term. But you saw that we still have the color spaces used 2.2 gamma, and this is just for consistency reasons at the moment, because we would need to change a lot of color spaces, and we thought to not do this, not yet. But we're trying to avoid the word gamma if possible. Okay, let's have just a look. If let's say I'm 5.3 and I want to render H.265 hardware encoded 10-bit QuickTime, I need to make sure that my color space tagging is set to automatic. I'm using the sRGB display, so you will see in the default in the default dropdowns the legacy sRGB tilde 2.2 gamma color space is gone. Also here, if you press Shift, you will see it's living here. It's live together with the 709 camera tilde 1.95 camera. I think I made a video a few years ago about that thing already. And then you're off to go. If you're using a display rendering transform that has an Office 100 nit DRT. Okay, I think that's it. Yeah, 45 minutes. I think we can, if there are any questions, answer them. Otherwise, I'm not sure. What, Andy, have you been busy in the background?
Yeah, a little bit. So till the end, there were a few questions coming in. One question is, how is the bright surround compensation called or applied actually in Baselight? So is that an option in the DRT?
That's a really good question. Yeah. So the surround comment, it depends really on which display rendering transform you're using. So you find the display rendering transforms that are the display rendering transforms family. They have this symbol with several S curves. That means that they have different different outputs for and different compensations, not only for the surround, but actually for the whole viewing condition. We call this the viewing condition. Cinema 48 nits, 108 nits, video wide. So this is wide gamut displays, 1000 nit, 2000 nit, 4000 nit. And it really depends on which display rendering transform you use, what kind of options the creator of that color management workflow give you. And or if you are one that does custom display rendering transform family, if you're image engineer or color engineer at a post house, you can register them yourself. And here the TrueLight Cam or TCam and TCam V2, they both have Office 100 nit compensation. To be fair, I think we are the only ones which come pre-installed with Baselight that actually ship with a DRT for bright surround. But maybe the others watching this now maybe also make one. I hope.
So there are a few questions asking about how to deliver content to phones. And so I guess the question is, how should they render approval files that are judged on a phone or a tablet probably as well?
Yeah, so I think the key is to use proper metadata, because there will be, if we take let's say the iOS devices, there is color management, a quite good color management running on those devices, because they all have different display color spaces. So the actual displays are different depending on models. So there are new ones which have also have higher brightness, and some are wider gamut, others older ones are less. So you cannot render for all of them. So you need to use correct metadata tagging to give the color management that works on the device a chance to do the right thing. So you cannot fight color management. You need to use it and to get it right. So I would suggest, from what I know, is to use the new sRGB display color space, add metadata tagging to automatic, and then I think it should do the right thing.
Yeah, and I think that also should answer another question that basically goes into the same direction, whether to use for Apple devices then the Apple Display P3, and I can maybe shorten that up, that if you use the sRGB display and automatic tagging, at least from our experience, it should work on Apple platforms because the color gamut will be managed on the device.
It's a strategic thing. It's like if that content is watched on one of the newer Mac hardware which uses Apple P3 display, then these devices are color managed, so they can deal with sRGB content. If we take out that flare compensation thing which lived in there before. But what if the same file is viewed on a legacy browser, on a legacy display? Then the chances are not so high that it's actually P3 gamut. So this, I would say, the safe way of encoding an image would be sRGB, because if there is no color management present at some stage, the chances are higher that the actual display that then shows the encoded RGB pixels on the monitor is something that approximates an sRGB display. But if you only have one DP and you do look development and it's a closed loop and you want to, and it's also from the look side of things, you want to explore the few colors that are that are beneficial to your look, then you could use the render specific deliveries for this as well. Sure.
Yeah. So that's also how I would see it. And there's one good question, which is about how do we deal with sRGB encoded images coming into the grading system?
That's good. Probably titles will still, because yeah, other softwares, motion graphics and visual effects software, they also have this kind of, at least some of them, they use sRGB just for the compound function, and then they have an alternative with a 2.2. They call it 2.2 gamma or something like that. So just to distinguish these two. For this reason, it depends. If you want to have an accurate conversion to your pipeline, then you should tag it as sRGB tilde 2.2 gamma, because that would then relinearize the footage correctly. That's why that color space is also still in the software accessible with a shift click. Then yeah, and I would, if you know that it's encoded like that, then yeah, use it and identify it as that. It's always the goal on the input side, and of the output side of things, always tag the color space correctly. So don't use color space either on the input side or output side for any creative reasons. It always bites you in the from behind at some point.
Yeah. There's another one. So if you're grading something for theatrical release and the client requires an sRGB master, what would be the best method to create it? And now the tricky thing is considering all the work was done using a DRT that doesn't have the brightness compensation. So if you didn't use TCAM.
Now I'm in the corner, like, well, you have, then I would do a trim, basically. I would do a trim which at least approximates what that surround compensation is doing. And to be honest with you, that only that part of the the surround compensation can be approximated quite good with a power law function. And there are ways in Baselight to do this without also changing the saturation and the use. Yeah, so you would probably do this manually. So you would do then something like 1 point. If you come from dark surround all the way to bright surround, then you would probably end up with a power modification of something between 1.15 and 1.2 ish. Probably 1.15 is something we found is good from dark to bright. If you then find that you're doing always the same trim, and you say like, oh, I have a satisfactory surround compensation for that DRT family, there's nothing that stops you from updating that DRT family with your edit and add the bright surround in there. So you can create, if for example you have a DRT family and it doesn't ship with it, you can extend it. you combine your edit with the one for, let's say, dim surround, and you create a new either GLSL formula or a new LUT if it's a LUT based. Most of the external DRT families are still LUT based, so you bake out a new LUT, you register the new DRT, and then you have it basically. Yeah, we can help you with this. So if you contact FilmLight support, then we can show you how to set up a custom DRT which has all the viewing condition compensations you need.
Yeah, maybe we have the last one, which is for remote grading at the moment. So if people are outputting basically one signal to their grading reference monitor, and another signal goes via a streaming provider. There are several out there to the customer, which has a computer display. And the question is, which viewing color space should I give to the client stream?
Yeah. So it depends on a few things. It depends on what the streaming service adds on into this equation. If we assume that it's a transparent transmission layer, which sometimes it is, sometimes it isn't, then you would use a dual color. Ideally, you would use a dual color space layout and give via one output, one SDI output, feed your monitor with what you have set up in your grading room, and use the second output with a different color space to match what the what your DP or your client is connected to.
All
Does it
right.
make sense?
Yeah, at least to me. So, I mean, now we're at exactly 1 hour. So, I mean, there are a few very specific questions which we'll answer in text after the webinar. And yeah, so we have a few more webinars in the pipeline. I think one of the next ones will be a daylight webinar in Spanish language, if I remember right.
Yep.
And so I say thanks for staying with us today, and see you next time.
See you next time. I hope it was informative, and thanks to all the crew behind that, making this possible, the webinar angels that helping us to set up all of this. Thank you.
Yeah, thank you. Bye-bye.
Bye-bye. And stay healthy.